Welcome to the second part of this video for 11-3, probability of multiple events. So now we're going to be looking at what happens when the two events are dependent. So we start with this question. It's from page 692, number 38. A jar contains 4 blue marbles and 2 red marbles as pictured below. Suppose you choose a marble at random and do not replace it. Then you choose a second marble. Find the probability that you select a red marble and then a blue marble. So again, the first thing we need to pay attention to is this independent or dependent? So there's a key phrase here in the question. When you see do not replace, right? Meaning we take a marble out and we leave it out. That is a hint that these are going to be dependent, because the first marble that you pulled out will affect what happens on the second round. Okay, so we're looking at dependent events. Find the probability that you select a red marble and then a blue marble. So we're still looking at and. We're looking at two events, the first event being red, the second event being blue. So the key here is that we're going to be using the same concept, okay? And is still going to tell me to multiply. And we are still going to be multiplying the probability of pulling a red marble times the probability of pulling a blue marble. The only difference is when we get to this blue marble, we're going to have to change the value we substitute in based off what happens on the first round. For example, so we have a total of 6 marbles in this bag. On the first round, right, we have a 2 out of 6 chance of pulling a red marble. So that's the probability of red. Now, what are we multiplying that by? Well, let's assume that we took out this red marble. Well, what is the new probability of pulling a blue? Well, now there are only 5 marbles left in the jar, 4 of which are blue. So the new probability of blue is going to be 4 out of 5. Again, it's being changed because we have already pulled one of the marbles out. We're still going to multiply these together. We're still going to cancel whatever we can. And we get 4 out of 15 as our probability. All right, so it's the same formula. It's just slightly adjusted based off of what happened in the first event. Okay. So now we have to look at some more definitions. Mutually exclusive events. So if we think about what it means, mutually exclusive. 2 events that cannot happen at the same time. They are exclusive. If one happens, the other cannot. So if we think about this in terms of the probability of these 2 events happening at the same time, the answer has to be 0 because it is impossible. Remember, 0 is for impossible. Okay, so for example, we have a deck of cards. If event A is aces, pulling an ace, and event B is king, those 2 things cannot happen at the same time, right? An ace is an ace, a king is a king. There's no such thing as a king-ace card. So those would be mutually exclusive, whereas hearts and kings are not. And why is that? That's because there's 4 kings in a deck, and one of those is the king of hearts. So it is possible to be both a king and a heart card at the same time. So these would not be mutually exclusive. So let's look at it from another perspective. If we roll a standard number cube, are the events mutually exclusive, meaning they cannot happen at the same time? So rolling an even number and rolling a prime number. So we have to think about the number cube. What numbers are even? We'll start with even. Well, on a cube, we have the numbers from 1 to 6. So the even numbers are 2, 4, and 6. So now, is it possible to be both an even number and a prime number? Well, the answer is yes. 2 is both even and prime. So this situation, these 2 events are not mutually exclusive because 2 is both an even and a prime number. What about B? rolling an even number, and rolling a number less than 2. So let's take a look. We're back at that list of even numbers. 2, 4, and 6. Are any of those numbers less than 2? And the answer is no. There's only one number on the number cube that works, which is 1, and that is not even. So these two events are mutually exclusive. Okay, so again, mutually exclusive means that they cannot happen at the same time. All right, so the second type of probability we're going to be looking at today is the probability of A or B. So notice the change of word in between. When you see the word or, I want you to start thinking of adding. Okay, so if we're trying to calculate the probability of A or B happening, then we need to find the probability of A, add it to the probability of B, and then if there is any overlap where they are happening at the same time, we have to subtract it. Okay, so probability of A plus probability of B minus what they have in common. Now, if they are mutually exclusive events, the formula gets adjusted slightly, and that should make sense because for mutually exclusive events, right, this value is 0. So it would be like we are subtracting a 0, so we don't need it. So for mutually exclusive events, all we have to do is add the probability of A and the probability of B. So to demonstrate this, let's take a look at this example. It's an example from page 690. It says, suppose you reach into this dish below and select a token at random. What is the probability that the token is round or green? Okay, so we're going to look at this in two ways. First, we're going to look at it just based off of the picture. The probability that something is round or green, well, first we need the total number of objects in the dish. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 total objects in the dish. Now, in order for something to be round or green, right? Well, let's take a look at the round ones. We have 1, 2, 3, 4. And the green ones, which is just the box. So that's a total of 6 objects here. So my probability here is 6 out of 9, 6 over 9, or 2/3. So now let's do that with the formula. Okay, we want the probability of round or green. Okay, so to do that, again, or means to add. So we need some sort of addition here. What are we adding? Well, first we're adding the probability that something is round. Then we're adding that to the probability that something is green. And we are subtracting any overlap of anything that is round and green. Okay, so let's take a look at this picture again. So what is the probability that something is round? Well, we have, again, a total of 9, and we have 1, 2, 3, 4, 5 round tokens. So that is 5 over 9. To that, we have to add green tokens. So how many green tokens do we have? 1, 2, 3. So that's 3 over 9. Right? Now, from that, we have to subtract anything that is round and green. So which ones are round and green? Well, we have 1, 2 out of 9. So we're subtracting 2 out of 9 from that total. So when you subtract these, or add and subtract these, we get 5 plus 3 is 8, minus 2 is 6. The same 6 over 9 we got when we looked at the picture. Again, that reduces down to 2/3. All right, so that's how the formula works. We're adding the two individuals and then subtracting any overlap that we have. So let's take a look at number 24 on page 692. It says, about 30% of the U.S. population is under 20 years old. About 17% of the population is over 60. What is the probability that a person chosen at random is under 20 or over 60? Okay, so we want under 20 or over 60, right? So we're looking at OR, which is adding. Well, that means we are finding the probability of under 20. We are adding to it the probability of over 60 and subtracting from it the probability of under 20 and over 60 at the same time. Now, you should be saying to yourself, under 20 and over 60, that's impossible. And that's because these two events are mutually exclusive. So since this is impossible, it's like subtracting a 0. We actually don't even need it, right? And so in the end, we're just going to add these two probabilities together. Under 20, 30%. Over 60, 17%. For a total of 47%. So you have a 47% chance of choosing a person at random that is under 20 or over 60. Let's take another look at another question. Number 25 on page 692. A standard number cube is tossed. We want to find the probability that whatever we roll is 3 or odd. Okay, so 3 or odd. Again, look at the or, means to add. We want to find the probability of 3, add to that the probability of odd, and subtract anything that is 3 and odd. Okay, so looking at the standard number cube, there are 6 sides, so there's going to be a denominator of 6. The probability of rolling a 3 is 1 out of 6. Great. To that, we're going to add the probability of something being odd. So how many odd numbers are there? There's 1, there's 3, and there's 5. So there is a probability of 3 out of 6. From that, we want to subtract anything that is 3 and odd. So obviously, 3 is 3 and an odd number. So we have a 1 in 6 chance that we roll something that's 3 and odd. So from that, we're going to subtract. So what happens? Well, the 1, 6 and the 1, 6 cancel, and we end up with 3 out of 6, or 1/2. So you have a 1/2 chance of rolling a number that is 3 or odd. Okay. So now, page 693, number 42, we want to determine if events A and B are mutually exclusive. Okay, so we're given the probability of A, the probability of B, and the probability of A or B. In order for something to be mutually exclusive, right, we need that the probability of A and B is 0. Okay, so if we think about the formulas that we have, P of A or B is what we're given. Well, that's equal to the probability of A plus the probability of B minus the probability of A and B. So if something is mutually exclusive, we will see that this A or B will not affect it, and that the probability of A or B has to be equal to probability of A plus probability of B. So let's check. The probability of A or B is 13 over 24. And that has to be equal to, so we'll put a question mark there, the probability of A plus the probability of B. So I'm going to use like denominators practice with my fractions. 24 is a like denominator, so we get 9 over 24. Like denominators here, 4 over 24. When I add those together, I get 13 over 24 is equal to 13 over 24. So since the sum of the two probabilities is equal to the OR, we know that, yes, these are mutually exclusive. All right.